and welcome to 16.3 Colligative Properties of Solutions. In this section we're going to define what colligative properties are and why we observe them. So first things first, what is a colligative property? A colligative property, let's go ahead and do the fill in the blanks here. A colligative property is a property that depends on the number of particles dissolved and not upon the identity of those particles. So once again, a property that depends on the numbers of particles, or just the number of particles, and not upon their identity. That is, when we dissolve different salts, when we dissolve different sugars, it's going to have an impact on the properties of the solutions. However, it doesn't matter which sugar or which salt we use, it just depends on the number of particles that ends up being in solution. Now, what types of properties are we talking about here? Well, three very important colligative properties are going to be vapor pressure lowering, and we'll remind you what vapor pressure is, and the consequences of that vapor pressure lowering, which will be freezing point depression, and boiling point elevation. Alright, so let's go ahead and jump in and see what's going on with these colligative properties. Well, first of all, vapor pressure lowering. Let's talk about what vapor pressure is. If we have a solution, we'll go ahead and do it over here. And we'll just say let's just say we have a pure liquid. And there are various particles in the liquid that comprise the liquid. Doesn't matter what shape those particles are at this point. What's going to happen is that some of these particles are going to have enough energy to escape the liquid phase itself, and it's going to go into the gaseous phase. All right, and if we put a lid on that, these particles are going to bounce around off the walls, and eventually they're going to crash back into the solution. Well, what happens is there's an equilibrium that exists where you have so many particles that go into the vapor phase or into the gaseous phase, and you have so many particles crashing back into the liquid phase. When you have the same numbers going up, and let's go ahead and do that in orange just so we can show, when you have the same numbers of particles going up into the gaseous phase as we have crashing back into the liquid phase, let's go 1, 2, 3, 4, 5. When those two are equal, the pressure that's exerted by these particles up here is called the vapor pressure. Now, some liquids have high vapor pressures because a lot of particles can get into the vapor phase. Some liquids have relatively low vapor pressures because very few of them overall will be getting into the vapor phase. But anyway, this pressure that's exerted by this vapor at equilibrium is called the vapor pressure. So what ends up happening is that these ions that are going to be in solution, or we'll just say that the solute particles, let's go back to our red color here. When you start dissolving something, and I'm going to actually change this to green just because we've already used red up there. Let's go green here. If you start putting in solutes, there we go. Those solute particles are going to be surrounded by water, by molecules of water. All right, and in this case, this is the solvent that we're using, the water. But it's going to be surrounded by water molecules, or let's just call it solvent molecules, because it doesn't have to be water. Whatever you're dissolving the solute in. Now this is going to reduce the number of particles that have enough energy to escape. Why? Well, because what happens is whatever the solvent is, it's going to actually be attracted to those particles, and it's going to try to keep them down in the solution. And so because now there's a force that's holding them down in the solution, fewer of them can actually escape into the vapor phase. If fewer of them can escape into the vapor phase, you've effectively lowered the vapor pressure. All right? Same thing, that's what these diagrams are showing over here. A pure solvent is going to have a relatively high vapor pressure because nothing except for the attractions of the particles to themselves are holding them in the liquid phase. However, once you put something in there, and that's those green particles right here and here, etc., those particles are actually attracting the water molecules and holding them down into the solution. And so fewer of them actually escape into the vapor phase. So anyway, that's why vapor pressure is going to lower when you put solute into some type of solvent. So this reduces the number of solvent particles that have enough energy or kinetic energy to escape as a vapor. Now, there are different things that you can add, or different types of solutes that you can add to the solutions. For example, glucose, C6H12O6. When you put that into water, it remains as one unit. And I'll just put a 1 out front to emphasize it, C6H12O6. For every one molecule of glucose that you put in there, it just stays together. You only get one molecule dissolved. However, if you were to put in something like sodium chloride, NaCl AQ is going to break up into sodium ions and chloride ions. Both of those would be AQ in this case. So you actually get two particles, as opposed to the one particle that you get when you put glucose in. And if you take a look at calcium chloride, CaCl2, is going to break up into calcium ions and two chloride ions to balance, because it's CaCl2, you get two chloride ions, so you get a grand total of 3 particles. So here's the deal. If you put one molecule or one unit of glucose in a solution, sodium chloride, and calcium chloride, you get more particles of calcium chloride than any of those. You get double the amount of sodium chloride as you get glucose. It is the number of particles that matter, and we're going to be doing those calculations in 16.4, where you'll actually see the effect of having 2 particles versus 1 particle versus 3 particles. But it is the number of particles that matter, not the identity. It doesn't matter if it's glucose or if it's sodium chloride. Just how many particles are actually dissolving. Here's the overall effect. When you lower the vapor pressure, here's a vapor pressure diagram. This is something that you guys would have looked at in chapter 13, where you have your solid, liquid, and vapor phase, and you can see what state of matter a substance would be in at various temperatures and pressures. Notice what happens when the vapor pressure lowers. Now, effectively what's happening is that this thing is lowering. But as that lowers, look what happens to the diagram and the temperatures at which things freeze or boil. When they freeze, this is the normal freezing point right here. Anywhere along this line is where the liquid freezes. Okay? But what happens is, as the vapor pressure lowers, that brings that diagram or that line to the left and effectively lowers the freezing point. On the other hand, this is the part of the line right here where the liquid would boil into the gaseous phase. Well, as you lower the vapor pressure, that effectively shifts that portion of the graph to the right, and it raises or elevates the boiling point. So you can actually measure the differences in the freezing and the boiling points, and that's what's called freezing point depression or boiling point elevation. Freezing point depression freezing point is the difference in freezing point or difference in temperature between the freezing point of the solution and the freezing point of the pure substance. And boiling point elevation is simply the difference in the temperature between the boiling point of the solution and the boiling point of the pure substance. And it all goes back to the lowering of the vapor pressure due to the attraction of the solvent particles to the solute. Okay? In the next section, we're going to take a look at the calculations, and we can actually calculate how far the freezing point will be depressed or how much the boiling point will be elevated. We'll see you next time in 16.4.